So hello all, my name is Theofilos Petsios. I'm a PhD student at Columbia University, and today I'm going to be presenting to you the work we have been doing on differential testing. This is joint work with Adrian Tang, as well as our advisors, Sal Stolfo, Angelos Kiromaitis, and Suman Jana. So I guess most of the audience must be familiar with differential testing. It's a very well-known testing technique, and essentially, with differential testing, we mainly try to target logic bugs in a similar way where with fuzzing we target memory corruption bugs. So to give you some example, you might have a series of applications that perform the same functionality. So suppose you have different SSL libraries. So these applications, they generally conform to the same standard or specification. So the intuition here is that if you observe some sort of deviation from this specification or standard, that's likely to be a bug in one of the applications. So what we do with differential testing is we feed an input to all of these applications, and then we observe their behavior to see if we spot any sort of deviation. And this is, of course, not applicable only to SSL libraries, but it's also applicable to compiler testing, or you could differentially test different JVM implementations and so on and so forth. Now, the key challenges with existing differential testing frameworks is that many of the tools that have been proposed are domain-specific. So they're not easily extendable to different types of applications. And often, they suffer from inefficient input generation. So our goal for this work was to mainly come up with a solution to provide efficient domain-independent differential testing in the same manner that modern fuzzers work. So to give you some idea, how can we achieve this domain independence? Essentially, one technique that has been shown to have to be very successful in this domain is evolutionary testing. So the way this works is that you start with a corpus of seeds, and then you pass these inputs to your application. And now the application has been somehow instrumented to give you some sort of information about its state. So whether you discovered something new in the control flow graph, or whether you have some sort of memory error. So you propagate this information back to your guidance engine, and in this way you get a sense of which inputs were actually most useful for your analysis. So you evolve your corpus in an evolutionary manner to basically make it occur more interesting behaviors inside your application. So if we wanted to come up with a differential testing framework that is generic, one can say, okay, we should focus on this input generation guidance. But how does this guidance engine actually comes up with interesting inputs? So to give you an example of how this works, let's think about a very well-known case study, which is the way code coverage is used in modern fuzzers. So suppose that this box here represents all the possible code paths in the application. So what we're going to do is we're going to maintain an input corpus of inputs that are actually interesting to us, and then we're going to be recording the per input coverage for this particular scenario. So essentially, if an input is interesting and it triggers some new functionality, it explores some new code path, we're going to be adding it to our corpus. So suppose we get this input 1 here, and we see that it exercises some portion in the control flow graph, and this is completely new, so we haven't seen it before. So we add this input into our corpus. We will come up with a second input, we exercise it into the application, and then again we see that we explore some new portion of the control flow graph. So we add this again to our corpus, and we keep doing this process until we reach a point where we exercise some input and then we discover nothing new. So this input gets discarded. So now the question becomes, how can we retrofit this particular mechanism, especially for differential testing? Because right now the question is, we have these generic fuzzers which work really nicely, but for differential testing, how can we come up with a same sort of approach? So there's 3 options that one can consider. One is that you can use a single application and come up with interesting inputs to be used for differential testing. So for instance, you fuzz open SSL, you see all the inputs that you get, and then you provide the same inputs to different SSL libraries. Another option would be to augment this engine of modern fuzzers and use global code coverage as your guidance. And the third option would be to completely redesign your guidance engine so that you can perform differential fuzzing this time. And in this work, I'm going to show you how the third option outperforms the other 2 options, particularly for differential testing. So the key insight for this work is that techniques that work well in the context of a single application may not be optimal for differential testing particularly. So, to show you why this is the case, let's go back to the previous example and suppose now we're using a global code coverage to differentially fuzz two applications. Now we take one input and we exercise this input and we see that we explore some portion in the code of both the applications. So that's really nice because we haven't seen these code paths before. So we add this input into our corpus. And now we keep doing the same process as long as we discover new code paths. Now we exercise a third input here and we see that we don't discover anything new in our global coverage, and normally we would discard this input. And likewise for input 4, we don't get anything new. Now, if you observe input 3, we see that it triggered some part of the code of application A and some part of the code of application 2. And it's the same for input 4. But if you observe these two inputs, we see that they exercise disproportionate code regions in the two applications. Now, if you think about the fuzzing process, this disproportion might actually imply that there is a difference in the handling logic between the two applications for these two inputs particularly. So the intuition is that had we retained these inputs in our input corpus, we would be able to find more discrepancies because we would push the evolutionary fuzzing towards generating with more inputs that would trigger this sort of discrepancies. So again, the relative program behavior is really important in this context. So in this paper, we introduce this notion of differential diversity, and we suggest that as a new means to achieve guidance for differential testing. So the main idea here is that we will obtain some sort of state information for the application, and you can do this in a white box manner at compile time, or you can perform dynamic binary instrumentation, or even in a completely black box manner. But then the state information will give you some notion of the behavioral diversity of the applications you test. So for instance, suppose you want to differentially test SSL libraries. You will take an input and you will feed the same input into all applications. And then depending on what you choose to formulate, depending on what metric you choose to represent each of your applications, essentially you will try to come up with the behavioral asymmetries for your exact scenario. So in the same manner in which in traditional fuzzing of a single application, you want to maximize, say, code coverage, all the total edges that have been accessed, so you want to maximize some sort of counter. Here, you want to maximize the behavioral symmetries across all your applications. So I'm going to present to you two examples of how we can retrofit the previous case of code coverage with a delta diversity paradigm and show you how we can get better intuition on the guidance. So suppose that instead of using just the global code coverage, you could keep track of the unique edges you have accessed in each of the two applications. So for input 1, you see that we access 3 edges in application A and 2 edges in application B. So we can have a tuple of 3.1 that denotes the path differential diversity of that particular input. And we see that for input 2, we trigger 2 edges in application A and 3 edges in application B. So now we have a different tuple of 2.3. And under this new paradigm, these two inputs are interesting to us because they result in something that we haven't seen before. So for a third input that actually results in a tuple that we have seen before, we can discard it. And of course, one can perform a completely black box testing. So you could say, I want to formulate behavior just based on exception messages or error codes, or even the return values of the tested applications. So for instance, you could supply an input to both applications and say, what is the return value I'm getting back? So if you get a 0, 0, that's something that you haven't seen before as a tuple, so this is an interesting input. If you get a 0, 1, and dead, again, you haven't seen this particular combination before. But then if you provide a different input for which you get again a 0, 0, then that's not interesting for your analysis and you can discard it. So in the following, I'm going to show you that this approach is actually domain independent and also can be efficient. So to do so, we implemented a prototype named NEZHA, and we also implemented different gray box and black box delta diversity metrics. And we built NEZHA extending libfuzzer so that people can actually perform differential testing for semantic vulnerabilities and logic errors, as well as crash-inducing bugs at the same time. And we also applied NEZHA in a bunch of different workloads so that to show that it can actually find bugs and logic errors in real-world software. So we tested SSL libraries as well as different PDF readers for logic errors and discrepancies, as well as different file format parsers. So to give you some example on our results, I'm going to present to you some of the cases of differential testing we did on SSL libraries. So what we try to do here is we try to find certificate verification discrepancies. So in this context, we're looking for a certificate for which one library says it's fine and it accepts it, and another library rejects it with an error. Now, in principle, that should not happen because the certificate should either be valid or invalid. But we applied NEZHA on different SSL libraries, and in this table you can see the pairwise discrepancies that NEZHA found based on the error codes that each of the libraries returned. So a number of 10 here between LibreSSL and OpenSSL denotes that we have 10 different certificates that NEZHA generated during the fuzzing process, for which one of the two libraries accepted it as valid, while the other library rejected it as invalid. So these are all unique instances pairwise. And of course, there could be some false positives here in the sense that some application could reject a certificate. Some library could reject a certificate because, say, of a weak cipher. So it could be a design decision. But in principle, we show that we can find both real bugs as well as cases for which we trigger these sort of discrepancies. So one can say, okay, how does this compare with domain-specific tools that could, say, perform certificate verification? So we compared NEZHA with FrankenCert, which was presented in Auckland a few years ago, as well as some follow-up work with NewCerts, that both tools are domain-independent and perform certificate verification. And we show that in the same number of generation, using this evolutionary domain-agnostic framework and the delta diversity guidance, we're able to trigger 52 times more discrepancies and 27 times more discrepancies than NewCerts and FrankenCerts, respectively, starting from the same corpus of inputs. And of course, one could say, okay, how does this compare to modern fuzzers like AFL or libfuzzer for this instance? So here we have two possible cases. In one case, one can say, I'm going to fuzz a single application and then provide these inputs to all the other programs we differentially test. And the other is, what if you adjust libfuzzer or AFL, say, to account for global code coverage? So we show that in the first instance, where we only fuzz a single application, if we use delta diversity as our guidance, we can trigger 6 times more discrepancies, whereas if we account for global code coverage, we still yield 30% more discrepancies on the same number of trials. So in the following, I'm going to give you some overview of the bugs that have been found by NEZHA. So these bugs are disclosed to their respective communities and patched. And of course, there are many more bugs in the paper. So for these domains where we applied NEZHA in, we compared the SSL libraries, as I mentioned, and also different PDF readers. And we thought, okay, let's try out different file parsers. For instance, what if we try ClamAV, the ClamAV antivirus, which is open source, with some other very well-used file parsers like binutils or the XZ library. So the first bug is a ClamAV evasion bug, which has to do with the way ClamAV parses ELF binaries. So if you have a malicious ELF binary, what ClamAV does is it scans its 5th byte to see if it's a 32-bit or a 64-bit binary. But if you corrupt this byte, ClamAV won't even scan the file. On the other hand, if you try with binutils, this gets loaded properly. And we found out that inside the loader, what happens is that the loader cares only if the binary is executable or not, and the whole header gets typecasted. So basically, as far as the loader is concerned, this binary can run without any issues. So you can get a virus and just corrupt this byte, and now you can have this bypassing ClamAV. And another bug, which is found by NEZHA, and I can present to you here, is a time confusion bug in LibreSSL. So essentially, for those of you who are familiar with the time formats in certificates, these can have two main formats. One is the UTC time and the GMT time. And each of these have a different length. So essentially what happens in LibreSSL is it ignored the actual time tag, time format tag, and it only looked at the length to determine what the date is. So essentially, if you could if you could provide the proper tag and a different length, you could treat libRSSL as if a certificate that was generated in the past is generated in the future. So it would reject a certificate as being invalid because it would see a date in the future for the issue date. So to give you some main takeaway conclusions, what we really want to show here is that a differential diversity is really a good way to guide input generation for differential testing and outperforms code coverage. And we also provide NEZHA, the framework that we wrote, which is open source on GitHub, so you're all welcome to try it out and fuzz your programs. And essentially, if you have the ability to perform differential fuzzing, so if you're developing an SSL library, there's no reason not to also perform a differential testing rather than simply fuzzing a single application, because you can catch all the semantic bugs together with the cross-inducing bugs. So with that, I'm happy to take questions.
I'm Alex Kampman, Qualcomm. So with the differential testing, you get this distance metric between different implementations. Right. Have you thought about looking at how that distance changes over time? So for example, all of these SSL libraries, did they start out to be mostly the same and then as feature set grew, they diverged? Or did they start out very far apart and then as they became more stable, kind of the differences shrunk?
So it really depends with what you choose to formulate, essentially, right? So here, you will again hit a plateau at some point in a similar manner that standalone application fuzzers hit a plateau. But there is a trade-off depending on what you choose to formulate under differential diversity, if it's going to be total edge coverage versus unique edges versus just different exception messages. So you can do different types of fine-grained tracking or coarse-grained tracking. So we explore some of these trade-offs as well in the paper. So it really depends on what exactly you choose to do, but you will hit a plateau at some point.
Okay, we'll follow up offline.
Sorry?
I'll follow up offline.
Any other questions? All right, let's thank the speaker.